So previously, we haven't gone over too much motion of a circle, except for uniform circular motion, which is just pretty much figuring out why an object stays in a circular motion. And as you know, in a circle can be measured as in degrees, which, as you know, a circle has 360 degrees. But also, a circle can be measured in radians, which is the ratio of the arc length to the angle it makes on the circle. So through that, the circle makes 2 pi radians per one revolution around. So that is, here to go, pi over 2, pi, 3 pi over 2, and then finally back to 2 pi, or we can call it 0 at the same time. So today we're going to go over angular motion and also the angular mechanics that come with it. So now we're going to be introduced to our angular terms, which is similar to, of course, the kinematic terms. First, we've got angular displacement, which is change in theta, of course. And this theta will be defined in radians, which is, as defined, the ratio of the arc length to the angle it makes. You can call it simply rad or radians. Along with displacement, we also have a velocity, which is a change in displacement over time, which is change in theta over time in this case. And that'll be angular velocity, measured in radians per second, or with this omega, lowercase omega, which looks like a W. And then, of course, with velocity, we have acceleration. Angular acceleration is delta omega over delta time, which is the change in omega over time, change in angular velocity over time. And that's denoted as radians per second squared, or with, of course, an fishy-looking alpha. So here's the angular kinematic formulas you can also use. They are almost identical to the ones we found in the kinematics unit. And you use them the same way. And I found this really good diagram that explains them. And here is them briefly. So what is moment of inertia or rotational inertia? This is an object resistance to angular acceleration and pretty much the mass distribution based around its axes of rotation. So this is what we measured in kilogram meters squared. And these equations are often given to you, so there's no need to memorize them. So now, what is torque? So torque is pretty much a force caused by a rotation, and it is simply defined by just tau equals r times f sine theta, which is pretty much explaining that torque, of course, is based on the force applied and the radius of which is applied as well, which means as the further out you apply the force, the larger the torque is. It is also defined as tau equals I times A, which is moment of inertia, times angular acceleration, which is pretty much Newton's second law. Keep in mind that conservation of energy also applies here in terms of conservation of angular energy. So the equation also looks very similar to the linear version, of course, and for the kinetic energy, it'll be pretty much 1/2 I times omega squared, which is very similar to the 1/2 mv squared you saw in the linear version. And also keep in mind, from this point on, you also will see, of course, kinetic translational energy or linear energy along with rotational energy, which you can use this for as well. Angular momentum conserves as well. So it is very similar as well, and instead we define angular momentum just as L, and it's equal to I times omega, which is moment of inertia times angular velocity. So angular impulse also applies as well, which it is delta L equals tau times delta T, which tau is instead the force given on rotation, which causes torque, which is here. And of course, as usual, a good diagram is with a figure skater, which they will change their moment of inertia in order to go faster, spin faster, have a faster angular velocity.